Now, you have his bio in your program, but I wanted to mention a couple of things, what it does not say. So first of all, let me mention the first sentence. Scott has studied theoretical physics as a hobby. Who does that? When I had the chance to intersect with Scott was when we were working on the Russell experience before. And I've been so impressed with his enthusiasm, with his commitment. And I remember Darren telling me about how he kind of knew that Scott was the person that was supposed to follow him. It's because he had so many notes in all of his science books that he knew he was really into it. Please join me in giving a warm welcome to Scot Vanderpool.
Today, I'm going to be talking about Walter Russell's concept. My name is Scot Vanderpool. I'm the Chief Science Officer of the University of Science and Philosophy. I've got about an hour, so this is going to be a brief introduction. We're going to talk about light, motion, and forces, okay? Now, I want to talk about concept versus a theory. A lot of times with science, you hear, Einstein's theory of general relativity. Theories are things that there's been experiments done these by multiple people. They've been, compared to nature, of observations of nature, and they turn out correct. So if you get enough of that, you can have a theory. But what starts before the theory is the concept, okay? So Newton had a concept that mass attracts mass, and it went on to become a theory. Einstein had a concept that space-time is curved. That went on to become the general theory of relativity. Russell also had a concept. That's what we're going to talk about today, the idea, a new concept of the universe. So all like science concepts, you have to start somewhere, right? So a postulate or an axiom, a postulate or an assumption. It's a statement that, it's not proven yet, but it's just a starting point, okay? So we have to start somewhere. And I'm going to start with 3 of Russell's postulates. So, and people at home the people who are here, you guys are already interested or already have experience with Russell, but there might be people watching this later that, this is brand new. So I say to those people, have an open mind, and we'll start with the postulates. These 3, you have to have an open mind and say, okay, I'm going to believe that these are true. Let's just pretend these are true. Then we can have a conversation, okay? So postulate 1 is that the universe is made up of only one substance, and that's light. Number 2, the universe exists in only 2 states, stillness and motion. Now I got motion in bold because that's really what we're going to talk about mostly here. And then there are only 2 forces, gravitation and radiation. And I remind you guys, keep an open mind, because we know in standard physics, there's 4 forces. But what if there were only 2? Gravitation and radiation. That's what Walter's concept says. So we're going to talk about that. These are some of the research books. Now, later, this video people will be able to watch this later, so you can pause it and you can kind of get this information. But these are, I've read all of these. These are great. If you're interested in the science, I highly advise you to read these books and the home study course. That's even more in depth than the books, okay? The next few slides are for you to pause later. I'm not going to go through all this, but this is like the puzzle pieces of Walter's concept that I think are needed for you to understand if you're going to learn it. Don't worry, don't try to read them all. You can pause this later. Okay. Now, they're also, he brings some new concepts. Once again, you can pause this later. I just wanted to get these on here for people to see later, because I just don't have enough time to go through all of this. All right. And here's some of the benefits of Russell's concepts, the real world benefits. I'll go over these briefly. One of the benefits of his concept is that it's one set of laws for all matter on all scales. It is a theory of everything. Like, we don't have that in physics yet. It explains things like the double-slit experiment, because matter follows gravitation. Well, I'm going to stop there. I need to teach you some stuff first before we go into that. But also there's there's less experimentation in chemistry. Like, we're going to know how all of the elements will work together. And these ones in blue are kind of my own personal opinions. I think that we will be able to precisely calculate where particles are. Like, there won't be a need for quantum mechanics probabilities and uncertainties. Like, we'll know exactly where things are if we use Russell's concept. And also, I think it'll explain gravity in a way that the motion of the stars and galaxies will be explained. There's not going to be any need for dark matter or dark energy. So these are big ideas, okay? All right, so let's go back. We're going to start on these postulates. So light, everything made of light. I like to say, Russell kind of describes it. Okay, so for the people who haven't really learned about his philosophy, there are plenty of books. I'm only going to do his philosophy a little bit here, but so Walter had a 39-day illumination where he got this knowledge, and then he was able to put it down into books, okay? And he kind of, the way I like to say it is there was kind of two universes. I'm putting in quotes because not really two universes, there's only one. But for understanding of his philosophy, one universe is like the universe that we sense with our five senses. This table, everything, okay? That's the sensed universe. The other universe, we can't sense it with our senses, but he says we can know that it's there. I like to think like the little voice that's like inside your head, like we all have it. You don't actually hear that like with your senses, but you know it's there, okay? That's just like one example. So
Yeah,
these two universes, we're going to talk about stillness and motion. Light, so remember, everything is made of light, and it's either in stillness or it's in motion, right? So we're going to talk about light and stillness. It can't be seen with our human senses. It's like, when you look out into space, you can see the stars. The darkness that's in between, that you can't see it, but you can perceive that it's there. I'm going to give you an example. So think of an indoor swimming pool that's been like closed for weeks. The water surface is motionless and is smooth like glass. Now, to describe these properties of stillness, I'm actually going to describe something that's more familiar, which is motion for you guys. So like, imagine we throw a little pebble into that still pool. What happens? Motion starts. Little ripples, little waves, right? And these waves, you can measure a wave. It has dimensions. Length, width, height, right? You can measure the frequency at which the crests rise and fall. You can measure the time it takes for a crest to move a distance, which gives you speed. I put move in quotes because in Walter's theory, light actually doesn't travel. It's an illusion. Well, I'll get into that later. Now, say you throw a big bowling ball into that pool. These waves are going to be different, right? They're going to be, the amplitude is going to be higher. These waves are going to have different dimensions than the little ripples from the pebble, right? So all of these different measurable wave properties are dimensions of the wave. They are dimensions of motion. And that's a really important concept in Walter's concept is motion, light in motion, okay? So in Walter's concept, there are 18 dimensions of motion. All right, more on that a little bit later. But I first have to clarify, these dimensions, they're not outside of our three-dimensional space. Like someone saying, "Oh, I've been teleported, to another dimension, like a parallel universe, like the multiverse kind of theory." It's not that. These dimensions are also not like abstracted, mathematical dimensions. It's not that either. We're talking about dimensions in the real world that we can measure. These are properties of nature. So I think that's one of the strongest parts of Walter's concept, is that it can be directly measured in nature. And so we can observe things and check it to see if it's right. So here are the 18 dimensions of motion. I mean, I'm going to go through these just briefly. We're all kind of familiar maybe with the first three, like distance, then you got area. You know, if you have two, now you got area. You add, you know, height, now you got volume. We've got time, which is just duration. We've got sex, which in my view is kind of like plus and minus polarity. I think Matt Presti's going to do a talk on that later. Pressure, potential, that's kind of a new one. I underlined potential because we're going to go into that a little more in depth in this talk. Then there's things like temperature, ionization, crystallization, valence, which has to do with chemistry. Number 12 and 13 are interesting because they are both dealing with time. Axial rotation, which is like, you know, you've got the Earth, it's got a North Pole and a South Pole, and it's spinning on its axis, right? He calls that speed time. And then you have, imagining the Earth orbiting around the sun, that's called power time, that orbital revolution. All right, next is mass, and then color. You know, you're kind of familiar with these. Number 16 is plane of gyroscopic rotation. This is another, I haven't seen this anywhere else in science, but like, so if you imagine a spinning top that you kind of you spin it, and then it can stand up straight, like 90 degrees. Like when it stops, it's just down. But when it's spinning fast, it's up 90 degrees. As it starts to slow down, you know, it starts to wobble, right? And so it will, and the slower it goes, the farther down it goes until it stops. So this angle from 90 degrees, you know, down, these are the angles of plane. He calls that plane. It's the gyroscopic rotation. And so that's an important dimension of motion to measure. Number 17 is the ecliptic. And that's kind of, if you imagine the Earth, North Pole, South Pole, you've got the equator around the middle. The ecliptic is really like the equatorial area. And he talks about that expanding or contracting. That is another significant thing to measure in terms of a dimension of motion. And the last one is tone or sound. So that's and all of those are measurable. And what's interesting is that all of these dimensions are linked together. If one of these changes in any little way, then all the other 17 also change. Okay, so it's really fascinating, and it gives us some insights. All right, so light and stillness. So now we can describe light and stillness compared to motion. So stillness is the opposite of motion, you know, therefore it has no dimensions of motion. There's no time, there's no beginning or end, there's no distance, because no one point is discernible from any other point. Like everything is infinitely the same. And I admit it's hard to fathom when you first kind of hear this, but this is part of Walter's philosophy. Remember I said those two universes? So the light and stillness is like this one universe that's just, it has no beginning, no end, no time, no distance. Every one point is the same as every other point. So like whether you're here or way thousands of miles, millions of miles over there, it's the same point. So that's just a unique thing to his philosophy that you guys can learn about. There are 2 points where he said we could perceive the light and stillness. So say you have two planets, planet P and planet Q. Right in the middle of the planet is a point of stillness. And then also between these two masses, there'll be a point of stillness. Let's see if I can do a little, see my pointer. Oh yeah, here we go. Yeah, so right here in between, there'll be a point of stillness. So as many of you probably already know, light in motion, it can be seen by our human senses. But it's important to understand that we can only see a portion of this moving light. And just because we can't see the light doesn't mean it's not here. Like we've seen, maybe you've seen this is like the spectrum of light, where you go from like, and we'll notice that like the human senses can only see this little sliver, this little white band here, okay? But just because we can't see this other moving light like ultraviolet, it's still there. It's just too high frequency for us to see. It's like a dog whistle. It's still there, but we just can't hear it, right? So it's important to just acknowledge that. So now we're going to discuss how light moves. And we'll talk about, this applies to both the moving light that we can see and the moving light that we can't see because it's out of our range. Not to be confused with the still light that we can't see, okay? So we're gonna have to discuss the forces that make light move. One of the major differences in Walter's concept versus traditional science is that, so if everything is made of light, remember that postulate, then that means light has mass. And that's a separation from traditional science. If they talk about particles of lights or photons that don't have mass, and that's in another section, like where we're looking at the standard model of physics versus Russell's, and that's only in a more in-depth version of this presentation. We can't do that right now. So we're going to talk about the forces, gravitation and radiation. So there's first one important thing that I'm hoping to get across to you. If you learn this will be kind of a gateway into his science. It's equilibrium versus polarization. So we're going to do a diagram here. Now we got two tanks of air, okay? And they are connected with a little pipe. The air can flow freely through this pipe, okay? So that means, this is at equilibrium. These are at equilibrium. And then we got some little pumping device here in the middle, okay? So actually, let me go back here. Just to reiterate, this is a universe of equilibrium and balance versus a universe of polarization, or more and less. Those are those two universes I kind of talked about. So you imagine two tanks of air connected with a pipe, and the tanks start at equilibrium. Now, when the pump is turned on, it's going to pump air, and I'll show you another. It's going to pump air from one side in this direction of this arrow. So now there's more on this side where we put the plus, and there's less on this side where we have the minus, okay? Right, so it pumps most of the air out of one tank into the other tank, okay? So now we have an imbalance. This is what we call polarization. So more air is now compressed into a smaller volume. In one tank, the air is now under higher pressure and is denser than it was before. And the air in the other tank is now at a lower pressure and is less dense. Okay, so we call this imbalance polarization. So let me see if does that make sense to you guys? Are you following me here? That's what a polarization is. Okay, maybe. Okay, wait, is there anyone who doesn't get that yet? Raise your hand. Okay, so imagine, all right, so you get the equilibrium state where there's just air in a room, like it's all kind of at the same pressure, right? If I turn on that pump, it's going to start making the air go this way. So now there's going to be way more air on this side than on this side. And that's all I'm saying, is that's the polarization, that there's more in one area and less in one area. Make sense? Okay. So yes, I mean, you could say this whole system is polarized. It's actually both tanks, the whole system is polarized because there's more in one area and less in another area. That's polarized. But what you're talking about in terms of this tank with the plus, Walter would say this tank is charged. It's been charged up, okay? I'll talk about that a little bit more later. Right, so now we're going to talk about gravitation and radiation. So look at these. So in a simple nutshell, gravitation, you got like a sun right here, or a planet, this circle, and all these arrows are pointing to the middle. Gravitation it's the inward direction toward the center of mass, okay? Versus radiation, if you think of the sun like light coming out of the sun, that's everything going out, away from the middle, into space, if you will, okay? That's kind of the general idea of the two forces, and these are the only two forces in nature. Is what Walter is saying. I always try to start like kind of simple, and then I'll just like reiterate it and make it a little more complex. So now let's talk about the description of gravitation. Gravitation is the force that causes light to move toward the center of mass. You know, I'm going to show you another, just something for you to keep in mind. Here, two planet P, we got planet P over here, planet Q over here, all right? So now when I read this, you can kind of keep this picture in your mind. Gravitation is the force that causes light to move toward the center of mass. Russell calls this direction north. He says north is positive. So the center of mass is the most north point and the most positive point. So Russell calls gravitation a positive force. So that's why we have the plus sign right in the middle there. Now radiation is the opposite of that. It's the force that causes light to move away from the center of mass. You know, Russell calls this direction south. South is negative. So the plane that's between the two centers of mass, here I'll show you that. It's like this plane here that's between the two suns or planets is the most negative southern point or south point. So he calls that that radiation is a negative force because of that. All right, let's move forward here. And just so you know, these two forces are always opposite. You know, gravitation and radiation. If gravitation is going this way, then radiation is going to go this way. Okay, it's like a rubber band. If I stretch a rubber band like this, as soon as I start stretching, like if that's gravitation, you know, pushing this way, well, radiation wants to push it back immediately. If I stretch it far, you got like a lot of gravitation. Well, then you immediately also have a lot of radiation trying to push back. Like as soon as I let go, it's going to slap back, right? So it's an action and reaction. So they're always there together, you know, in opposition. So all light moves in a curve. Specifically, it follows the path of a curved spiral, and it always has a specific cycle. I'm not going to talk about the cycle right now. We don't have time. We're going to say that light starts as a base of a cone. Now, I need to give you, an example here. You guys, like in a bathtub, when the water goes down the drain, there's that spiral, okay? It's a vortex, and it's in a cone shape. Like it starts wide and it gets smaller and smaller, you know, till it goes down the drain. So that's what we're looking at here. You know, on the bottom here is like a spiral going down, down, down the drain, right? And it's the same thing on the upside, is that spiral. So when I say, and it gives a cone shape, see this cone shape. So when I say light starts as a base of a cone, it's starting on this two-dimensional plane that's right in the middle here, this 2D plane. All right, so now you kind of have that graphic in your mind. I can read this. So light starts as the base of a cone, and it extends spiraling outwardly, you know, away from the 2D plane, out this way up and out this way down. It's a 3D spiral vortex, and it's the force of gravity causing this cone-shaped vortex, and it compresses light into a smaller space. As light is compacted into a smaller volume, it becomes more dense and under more pressure. This plane, you're going to see this throughout my presentation, this kind of peach-colored two-dimensional plane here. Just remember that guy, okay? So that guy is the plane of equilibrium, or it's the southern inertial plane. Now at the top of the vortex, that's north up here. And at the top of this vortex, well, I guess it's going down, that's also north. You know, normally we think on a map like north is up and south is down, but in this case, south is in the middle and north is at the ends of the cone. Okay? Here's directly from the Universal One. Walter says, all direction is curved, all motion is spiral. This would be like you looking down the drain as the water spirals down the drain, okay? And gravitation is what's taking it down the drain, but radiation, in 180 degrees, it wants to go the opposite direction. All right, so now we're going to talk about three-dimensional polarization. Whew. All right, so here we go. You remember this, guys. This was our equilibrium box, right? With our, you know, more and less, that polarization that we learned about. And remember this guy. Now we're going to start to put it together. So now I'm going to do three boxes. Same thing. We're starting at equilibrium. These pipes are open. The air can flow freely through here. It's all at the same pressure, okay? But when we turn the pumps on this time, one pump is going to pump this way, and the other pump is going to pump the other way. Now we've got less in the middle and more on the outsides, okay? So what we're going to do is remember this guy, this double cone thing. We're going to put him on here, turning him to the side, and show you that this is how the pumping action works. So gravity is like a pump. It's going to compress things towards the cone apice, the points of the cone, here and over here. And in the middle, there's going to be less, okay? More on the outsides, less in the middle. So it's the same thing here. Now we've got our two planets. So we're going to start to see how this concept of gravity is working in our universe, our solar system. Like these are actual planets here, okay? So we put the cones here. This is gravity. This is what happens. Gravity pushes towards the center of a planet. You know, the cone, that spiral vortex compresses things towards the center of the planet. Same thing over here, towards the center of the planet. And in the middle, there's less stuff. And that's why there's darkness in between the planets, okay? There's still light there, but it's just so spread out, it's beyond our senses. Okay. So sometimes one spiral vortex cone meets another spiral vortex cone, and when the two vortices meet, light can become concentrated in such a small volume, it becomes dense enough that our senses can start to see it where we couldn't see it before. Here's kind of a picture from the universal one of like two of these things meeting. Now light gets to a maximum point of compression and density and pressure, you know, that like in the center of the sun, it's got to radiate somehow. It's got to come back out. And it radiates in a spiral and becomes less compressed and less dense. It's the force of radiation that causes it to spread out like a flat pancake-shaped spiral. You think like the Milky Way galaxy shape. So I'm going to show you here. So this, I love this diagram. To me, this is the shape of gravity. You've got in the middle, you can see a cone on the top here, and then you can see a cone on the bottom. They're meeting in the middle, okay? They're bringing light, winding it up into this center mass. But then it's got to go somewhere. So what happens is it shoots out the sides, you know, as rings, you know, and it ends up going back to where it started from. Here, I'll superimpose. Remember this, our little friend, the two-dimensional plane. There's one up here as the base of a cone, and one down here as a base of a cone. And I apologize for this next graphic, but it was the best I could do, but I hope you get the idea. So we're gonna see the spiral in there. Can you guys see that? I've got the, you know, the spiral one coming down and the spiral one coming up. It's kind of hard to put that in there, but I hope you guys can see that. Now how does this look in space? Walter drew it for us. We see spiral like the Milky Way. This is if you're kind of looking down on it, I guess. But here he drew it if you're looking at it on the side. And look, he drew the cone, the spiral cone. You know, one is here. See, here's our little two-dimensional plane guy, the base of the cone. It spirals the light up, it winds the light up and brings it here. And then this one over here, winding the light up, bringing it here. It brings it all to the middle. And then what happens? It's got to go somewhere. So it goes shooting out the sides. All right. And that's how you get like this shape. And it ends up going out the sides. And then what does it do? It goes back to where it came from where it started. So light ends up back where it started its cycle to then repeat again. So how does this kind of happen? We got to talk about three-dimensional vortex motion now. We see our same guy here, but Walter adds something called the cube. All right. So now I love this graphic that he did. He shows, see these two arrows here? You can imagine one as gravitation, say, coming down. Then you got radiation, which wants to go 180 degrees against it. Well, it's like they're playing a game of chicken. They can't run into each other. So what happens is they turn right at the last minute before they crash, right? And so what happens if we put a cube here, if this happens in a cube, this is what happens. They have to turn, so it starts this spiral motion. And it just so happens that it follows kind of the path of least resistance in this cube, you know, and it goes towards the corners. So, when you have two vortices meeting, it really kind of more looks like this. So you got one over here winding up and meeting this other one over here winding up. And you'll notice that he has these numbers 1, 2, 3, 4, and 4, 3, 2, 1. These lines, this is what I talked about with the dimension of gyroscopic plane. You know, when I said you have the top spinning and it'll either fall down. So he shows us that these planes, they're important in his concept. They have to deal with chemistry. These are just locking positions. It just so happens that like things lock in that position. He has something called the formula of the lock potentials. Let's see. Now let's see what it looks like in more of a three-dimensional thing. Now we've got a cube here with a spiral. It's spiraling up towards the corner of the cube. We've got an adjacent cube over here where it's spiraling up towards the corner of the cube. They meet here. So this is where all the mass would be. This is where like a sun would be, okay? And once again, he draws these planes, you know, the 1, 2, 3, 4, 4, 3, 2, 1. That's just something that's significant. I don't have time to go into that, but it's something that's significant in his, when it comes to chemistry. All right, it's worth mentioning that Walter Russell had to choose terminology, you know, to describe his concept. Sometimes he used words that already had meanings in science, and he changed the meanings of those words for his concept. So it can be confusing. I just wanted you guys to know that, like, if you go to start reading some of his books, you know, so, and I'll try to clarify, like, for example, the term magnetism, he uses this term to describe the radiation force, okay? And then the term electricity, he uses that to describe the gravitation force. So he likes to set up, you know, electricity versus magnetism. I just think because that's what was going on back when he was around. But so I like to use gravitation and radiation instead of saying electricity and magnetism. It's just a little more confusing. Same thing with magnetic. He talks about magnetic versus electric. He'll say that magnetic, he uses that term to describe the unmoving still light versus the moving light he calls electric or electricity. Okay, so that's once again where he's putting this electric and magnetic just because they're kind of opposites. But so just to try to clarify that for you guys. And one last thing, which I thought also was confusing, was the way he used the term charge. Okay, and I'm going to show you, remember this when we learned about this polarization. So this box here would be charged, okay? And he puts a plus there. So some people would think, okay, it's positive charge, but it's not. So over here, you've got a minus, but this is not negative charge because you can only charge that by putting more. Now you can discharge this and it would go back to equilibrium, but the way that Walter uses charge, you know, he just says, you know, it's like describing more or less of something going from 0 to maximum charge and then back to 0. It can never be a negative charge like that. He says that would be like saying silent sound. Okay, well, let's see. that's the end of the presentation for now. How much time do we have, Kim? Do we have till?
So you still have some time and we can field questions.
How much time do we have?
You always want more.
I mean, because I do have one or two more concepts that are a little more advanced. That's kind of was the basic stuff. So,
All right, so let's pause for a moment. And
Yes.
Let me breathe in for a minute.
Let's
just
pause.
breathe in, and I'm sure there are some questions here within the audience.
Do you see any way that the different forms of your magnetism could describe anti-gravity?
yes, actually, that is the next thing that I was about to discuss would describe that actually.
Okay. All right. Well, you're setting up. Did he pay you before lunch?
That was great. That's
Did he
perfect.
pay you?
Okay, in terms of temporal or time base,
Yeah.
the two vortices, the gravitational and the radiative, occur simultaneously?
Yes. Yes. And sorry, I didn't describe that very well, almost just to try to be easy on people. But yeah, actually, gravitation and radiation, they happen simultaneously. Like I said, the example of the rubber band, as soon as you start an action, the reaction is like wanting to happen, immediately. Like they go hand in hand. So yeah.
Other questions? Yes, Margaret.
Would the charging motion be male and the discharging be female?
Yes.
Bingo, you win.
Bingo.
Pass
Ding, ding,
it on,
ding.
you'll pass it on back if you can pass
There's
it on
someone in
back-
the back
pass
there.
it behind you. To go all the way to the back row, just pass it on back there, please.
When you said light doesn't travel, and you were going to come back to that, and maybe you did, but will you say what you meant?
Yes.
Okay.
I think that is in the next more advanced section. So
okay.
yes.
So Scott,
Yes.
is it the
gotta wear a
case
watch.
then that light travels from the corner of each of the cubes to the next cube?
No. Yes and no.
Is that the mechanism by which?
So okay, I'll describe it. Actually, I mean, I have diagrams for this in the next section. Like this is exactly what I'm about to explain.
All right, you
If-
got 13 minutes. Go
Okay,
for it.
let's go.
He
let's
did
go.
pay
Okay.
me, so.
All right, so for this one, we're starting right here in 3D, a cubic wave field. You got one cube here, you got another cube here. So I'm gonna let you look at this. Ooh, okay. So on this side, we have, imagine gravitation, because you can see like these rings are going in towards the center, right? We can all see that. And on this side, the rings are going outward, away from the center. This is like radiation, okay? And now what happens when we put these two together? This is what happens when you overlay them together. Now, if you notice, you can kind of look in the center and you see it's alternating between like a white circle and a black circle, okay? Now, what I'm gonna do is have you realize that when you're seeing this is just a two-dimensional version. But remember, we wanna do this in 3 dimensions. So what I'm gonna have you imagine is that if you imagine a cube and the center of a cube, now instead of seeing this in 2 dimensions, just like as rings, if you could imagine this as a sphere, okay, so that you have these, like the sphere all around, like is going towards the center. Okay, if you can imagine that side as a sphere going towards the center, and imagine this side as a sphere, but going out radiatively, like out in all directions. Okay, and so then now when we get to this, we have to imagine this as in 3 dimensions as a sphere. So it's pumping, okay? It's a spherical heartbeat, if you will. And if you can imagine this sphere like in a cube, right? We're still looking at, like one cube here and another cube here. But in each cube, we have this going on. We have this 3-dimensional pumping. It doesn't leave the cube, it's just pumping in its cube, okay? So to address the light not moving. Yeah. Sorry, that's yeah. Okay, yeah. I think we got the point. Right. Okay. Right. We are not. Okay, so the example that I like to use in terms of light traveling is if you guys have ever seen, like at a big sporting event, there are people in a big stadium and they're all in their seats and they can do something that's called the wave. So it's like if everyone just stands up and then sits down like at the right time, then there's an illusion that there's a wave traveling around the stadium, okay? That is the illusion of light traveling. It's analogous to that, because you have to think each person is only in their seat and they're just pulsing like a heartbeat up and down. Okay? When we have our three-dimensional, as we, go back to that, remember this guy pulsing in a three-dimensional sphere? It stays in its wave field, and it's just pulsing in its wave field. But there's one wave field here, and there's another wave field here pulsing. And then there's another wave field and another wave field. Okay, they're all like adjacent. So if they pulse just right, there'll be an illusion that light is traveling. Okay, so in Walter's concept, light doesn't actually travel, but it's an illusion of motion that we see with our senses that it looks like it travels. Question. Wait, let's get you on the microphone. Yeah.
If I stand up and sit down, then she's signaled for her to stand up and sit down. So there's
Yes.
some sort of information, I'll call it, going from one to the other.
Yes.
But literally, I'm not moving this way and that way. I'm only going up and down.
That's right. That's right.
So will it start in one cube and then that somehow signal to the next cube and to the next
Yes.
cube and the next cube?
Yes.
Is that how it works?
That's a great question. Perfect question. So yes, when an action starts in one cube, so say we're in this cube, when an action starts in this cube, and now this is just something unique to Walter's science. And it's, to me, like one of the most incredible things. And for me, like the hardest thing to believe. But like he says that if something starts here, it immediately affects everything in the universe. Like he says, you can move your little pinky and you're affecting a galaxy billions of miles away. Okay? So, and it's clearly faster than light travel. Okay? To me, it blew my mind. But so yes, when something happens in one place, it happens everywhere. And that's kind of the universe of the still light. Something happens in one place, it happens everywhere. So the whole universe is connected as one. Wait, we had a question over here and then one over there.
So this is what's referred to as the universal heartbeat then?
Exactly. That, or, that other hypnotizing looking thing. Yes, that's the universal heartbeat.
Action and reaction is simultaneous.
Yes, because gravity is like the action and radiation is the reaction. They're actually simultaneously, and they're happening simultaneously, in that heartbeat.
So therefore, light does not, as you were alluding to, light does not travel. Its presence is everywhere all at the same time.
Yes, you got it. Yes, it doesn't have to travel because it's already everywhere. And that's what, like in Einstein's theory of relativity, he said light moves the same for every observer, no matter like how fast you're going. When I was first learning that, I was like, how can that be true? If I'm going this fast and I shine a light, I'm going faster than that guy. But if light is already everywhere and it's only just pulsating, yeah, no matter what speed you're going, it's gonna be the same for everyone. Okay, I want to hold off on questions there because I want to try to finish this more advanced. Okay, we're going to look at gravity, Newton's gravity versus Russell's gravity. Now we remember the whole equilibrium more and less with the tanks. We remember this, that we had like an imbalance between the tanks. So now we're gonna look at equilibrium and polarization in terms of things like a battery. Some of this, okay, let's see. I already went over that. Some of this is going to be a little just kind of intuitive. I don't have time to explain the exact function of this, but I think with the diagrams, I'm hoping you'll kind of see, just intuitively get it. So if you have a battery that have, you know, a plus charge on one side and less charge on the other, it's polarized. This is kind of what the symmetry would be like with this AB static equator. Now, if we change that to like an unequal volume, where we make this really small, but we make the other side of the battery really big, you're gonna get this equator that's more curved, and the symmetry is gonna look more like this. Now, I hope you guys can get that intuitively or by the picture, because it's really hard to explain. We don't have time to explain it. But the point of this is that now if we look at a bar magnet, okay, we've got our little two-dimensional plane here. You know, a magnet is just some metal, a piece of metal, and it doesn't become a magnet until it's magnetized. They take a piece of metal, they wrap a coil of wire around it, they run current through the wire, and then that magnetizes the metal. So what it does, it pumps potential to one side and to the other side. Now we've got that, it gets polarized essentially. So that's why, you know, you can pick up something on the end of a magnet on either side, but not in the middle. Now, Walter takes it one step further and he goes, okay, imagine this magnet. Now we're going to fan it out and it's going to look like this. It's the same magnet, but just he made this end wide and this end small. He said you could pick up a nail over here, but over here things are wider. You couldn't pick up a nail, but if you ground the nail up into powder, you could pick up the equivalent's worth of powder of a nail on this side. But there's a difference in potential. Like over here, there's a lot more. Over here, there's a lot less. Now, if we imagine that same fanned out magnet, like two coming together like this, remember there's more here in the middle and less on the outside. It's this polarization. This is like the planet Earth is right here. There's more stuff in the planet, but then outside around the outside, there's space. There's less stuff. And what that means is that everything has a potential position. This is a direct quote from Russell. He says, every potential has a balancing potential position somewhere in the universe. What he's saying there is like, if I have a thing, it wants to go where its surrounding is the same potential as it. Here, I have something to show you. Here's an example. All of these things are different things. They all have their own kind of density, their own potential. And they, like in the middle there's I think, what is that? A cherry tomato, it says. And you can see the cherry tomato is floating right in the dish soap, apparently. It wants to go, their potential is the same, or their density, if you will, is the same, okay? Whereas a ping pong ball, it's mostly air, so it's gonna wanna be up here. So he says, you know, everything has its balancing point, and it desires to find that position. And desire to find that position in every creating thing, and any restraint exerted against, like to prevent it from moving to finding its balancing potential, can be measured as weight. Like that's what weight is. It's just something, when something wants to go somewhere and you don't let it, then it'll exert a force, and that's what we call weight. So the interesting thing about this, so his theory works on all scales. So this right here is kind of a smaller scale, but if we look at this, this is what happens. This is the larger scale. The planets are the same as, you know, this over here. You've got the sun down here, which is the highest potential in the whole solar system. And as things get farther out away, they get less and less potential. Less dense, exactly, less dense. And that's why the inner 4 planets here, you know, from Mercury, Venus, Earth, and Mars, they're rocky. They're solid. You get farther out, now all the planets are gaseous because they're less dense, they've expanded. So Walter's concept of gravity, this is what I'm hoping that you get, that it's actually the way that gravity winds up light into more dense things, and radiation unwinds it into less dense things. That's what we call, he called it potential. So I must have missed a slide, but I'll just explain it. So like potential, an example of potential is like a gas. A gas is very low potential. Then next would be like water or like a liquid. That's higher potential. And then you've got a solid, like a rock. That's the higher potential. Okay, so things will try to find their balancing point. And that's really, in Walter's concept, that is what is causing gravity. Like everything that you see around us is because of its potential. It wants to find its potential position. And that's what really is controlling everything. So, so let's see.
Could you go over the ant and elephant example of the volume change and the chart of exactly the same?
Oh, yeah, yes. Okay, so, oh, I wish I had a graphic for that. So you're referring to, so Walter talks about a constant, that there's like an energy constant, and how would I describe this? So everything has to be balanced. So if you, for example, have, I guess, an elephant on one side of the scale, you could have a little ant on the other side of the scale, but there would have to be, you know, thousands of ants or whatever, a million ants in order for it to be balanced. I guess like, I guess the closest thing I have to that would be, this is probably the closest thing I have to that. Okay, so over here, this would be kind of like the elephant. It would be very compact, very dense. So it extremely dense. Yeah, exactly. So it could affect a solid object like the nail. Out here, it's extremely tenuous. So it's basically like the bunch of little ants, okay, versus the big elephant. But if you imagine like a seesaw, you know, these two, they balance each other out. It just takes, you know, many more ants versus like one elephant. That's not the greatest explanation there, but I hope that makes sense. There's a great, yeah, are we running on time? There's a great, in the universal one, oh, there's a great graphic for that. But anyway, I think my time is up. So we have a question. Yeah, so please, yeah, I would like to say, please come talk to me if you have questions. I would love to talk with you about all this stuff, and you know, and I can answer questions and talk to you about this. So, but I think my time is up.
We got a question from our
Okay.
Zoom participant.
Yes, I just wanted to get one question in from our Zoom participant. Sydney asked, what are the corpuscles mentioned by Walter in describing light and units of light?
Okay, right. So Walter talks about, you know, that light is in a wave, but these waves, they all have different properties. And it's my understanding that the corpuscles that he's talking about, they're waves, but they have the properties of like particles. The example I like to give is the two-slit experiment. If anyone's familiar with that, it's like they tried shooting what they call photons through two slits. And when they hit the other side, there was an interference pattern. They were like, how can, you know, an interference pattern is a wave property. How can this be? And I essentially think that from what I described to you about gravity, like those spirals, it winds up matter. Once that matter is kind of wound up and you can see it like a planet or a particle or something, it's still going to follow along with the wave of gravity, like a log following a stream. That's a good example. The gravity is like the stream. We can't see it, but it's there. Walter says it's there. And we can see that it's there because all the matter that we see is following, everything is going in a spiral. It's turning. It's following that current of gravity. And so like when they shoot in the double-slit experiment, when they shoot particles one after another, what ends up happening is as they accumulate on the other screen, it turns into an interference pattern. And that was a mystery. I was like, why is that? And Walter's the first one to describe that. It's because those little corpuscles, you know, they're waves, but they just have the property of little particles, just like a planet. You know, it is a wave, but it's been wound up enough that it looks like, you know, it's like a particle. Okay, so this works on all scales. But like, if you send those particles through those slits, you don't see the wave of gravity, but it is following the wave of gravity. So when they all build up on the other side, it looks like an interference pattern because all those little particles were following the stream of the wave. So the wave is there, and that's what you know. Once you build up all those little particles, then the wave becomes discernible. Like it's there, even though we can't see it. It's there, and that's kind of like the proof of it. From, you know, if it wasn't there, those particles will just go through, and there would be no interference pattern. So, right, that proves the wave, right? And so when you think of Walter's concept, it's like a good explanation as far as I'm concerned. That like, oh, so there's this whole wave that we didn't know about, you know, that like that's there, and it's really oh man, let's see if I have one last quick example of the wave that's there. Oh yeah, there it is. You know, if entropy was true, then like if you release like a gas in this room, it's just gonna diffuse and go to disorder, right? And that's why we think that the universe is gonna die a heat death, because it's all just gonna radiate out and be gone. But the spiral vortex does something quite unique. It can take all those random gas molecules that are up here in the sky, and what does it do? It turns it into a form, a very discernible, organized form. Science doesn't know about this. We always think it's all gonna blow apart. But nature is showing us right there, no, it can come back together, okay? And so that's why in Walter's concept, the universe is sustainable. There's the downhill flow of energy that expands outward, but then there's this invisible uphill flow of energy that takes the outwardness and brings it together. I've heard that term, and I can't comment on it. I'm sorry. But right. So there you go. So it's a two-way universe. It's a two-way universe. There's the expansion outward, but this is the invisible part that they don't see, is the contraction inward, because they don't see it until it winds up enough till it gets so dense, and then we see it. It's almost like, you know, up there when the gas is far apart, you might not actually see it, but once it gets down like here, you definitely see it. So that's right. When it's actually, in his concept, it's a two-way universe. So yeah.
Of what he's about, please join me in thanking Scott.
All right, that's it. All right, thanks, guys.
Can I hold your universal one? Can I hold your universal one?
Oh yeah.
Sure. So I'm going to ask if you would, Joey, show Scott's picture right quick. I want you to see when we're young as a child, you just never know where life is going to end up.
Oh yeah.
And I want you all to see Scott from a long time ago.
Do I need to do anything on my end?
No. There you are.
There I am.
All right. So look how far we've come, and when you
Oh my
feel the
gosh.
heart and the passion the passion of what Scott has there. And I asked him because I wanted to show you the thing I want you all to know, as much as the science can sometimes be overwhelming, everyone here are students who care about this learning and about bringing it to life. This man, this is his copy of the Universal One. So,
Oh, yeah.
so for any of you that find this interesting and want to someday be one of these that are up here presenting, please know that's possible.
Oh, yeah.
It is people that walk in here and have a passion for what it is. And I wanted you all to see that along with so many of your books.
These are, I recommend both of these books, The Universal One and Atomic Suicide. They're great. They're answering all your questions about this stuff. It's amazing. If anyone wants to get in touch with me, 3dfrequency@gmail.com. And also I'm going to be on YouTube, 3D Frequency at YouTube. I just wanted to get that on there. So, you know, and for people at home, you can reach out. I'm on Twitter as well at 3D Frequency. So 3D Frequency is everything. If you ever want to get in touch with me, please reach out by email or look for some of these videos that'll be on my YouTube channel or on philosophy.org. Thank you.